Hello, everyone. It is really my great pleasure to be able to invite Professor Buongiorno to give a seminar at NPRE. So Professor Buongiorno is the Temple Professor of the Nuclear Engineering Department at MIT. He's also the director of the Keynes Center for Advanced Nuclear Energy Systems. And also, he's also director of Science and Technology of the MIT Nuclear Reactor Lab. So I have known him for a very long time, since when I was a graduate student. In fact, during that time, he served the role as a director of graduate studies or associate head, kind of like my role in our department right now. So oftentimes go after him to ask for different kind of signatures. So he is a world-leading expert in the area of reactor safety and design, two-phase flow and heat transfer, as well as nanofluid technologies. So he has been given many awards, including lately the ANI's Outstanding Teacher Award, MIT McVicker Faculty Fellowship, the ANI's Landis Award, the ASME Heat Transfer and Best Paper Award, and ANI's Marker Mills Award. So he's also a fellow of the ANS, along with many other members of different board. I'm not gonna go over all of them. So in the time of interest, let's welcome Professor Buongiorno. The title of his talk is the need for radical innovation, which we cannot agree more. Please, Professor Buongiorno, the floor is all yours.
All right, thank you so much for the introduction and for inviting me. We commented already earlier today. Would have been nice for me to be there in person. It will happen. For the time being, we have to be content, I guess, with Zoom. It has been working well, I have to say, and hopefully today also will be a good discussion. So the format I'm going to follow is a roughly 40-minute presentation. If there are any burning questions, I think you can use the chat, and Yang, please monitor so you can interrupt me if there are any clarifications needed. If not, I would ask you to maybe keep the questions at the end so that we can have a Q&A session there. So I'm going to argue in this talk that if nuclear is not just to survive, but to thrive, particularly in the US, and I would say also Western Europe, similar situation, there is a need for change. The business as usual model is just not going to cut it. And we'll see what kind of change I'm going to propose here. So let me start, however, by stating what I think is the value proposition of nuclear in a world that seeks to decarbonize its economic system. Well, you may or may not know, nuclear is already and has been for a long time the largest source of emission-free electricity in important regions of the world, such as the US and Europe. This plot here shows the share of carbon-free electricity, so you only include nuclear, hydro, and other renewables. Worldwide, it's about 50% hydro and then 30% nuclear, 20% wind and solar. In the US is a little bit over 50% nuclear and then the other two. In places like China, they rely disproportionately on hydro. And in the EU, similar to US, and a place like the Republic of Korea, where I gave a similar presentation, nuclear accounts for almost the totality of their carbon-free electricity. So nuclear already plays an important role in our clean energy infrastructure. What are the trends? Well, we see certain growth in Asia, in particular, China, India, Russia, also the Middle East. And frankly, at the moment, we're seeing a decline in Western Europe, in Japan for obvious reasons, and the United States. It's interesting, the debate now about decarbonization of the electric grid has many different positions, and sometimes it's hard to sort of understand where the truth or where reality really lies. So I like to use this slide, which is from a study conducted in Europe a few years back, and to show the value of nuclear and renewables in decarbonizing the electric system. Europe is an interesting place to do a clean analysis of what technologies work, because it's 20 plus countries. Each country has chosen a different energy mix. However, they're all more or less integrated in a big continental grid. And so you can really see what worked and what didn't work. So that first plot there shows the share of essentially solar and wind renewables generation over a period of 1 year. And the average in Europe over that period was about 20%. And there were 6 countries that are at or above that average. They are Denmark, Ireland, Germany, Portugal, Spain, and Finland. So those, by definition, are the countries that have invested the most in solar and wind in Europe. What I'm going to show you next is a list of the same countries, but now they're ranked according to the carbon intensity of their electricity sector. Carbon intensity is the amount of CO2 emitted per unit electricity generated. So the units there are grams of CO2 per kilowatt hour. And obviously a low number there is good. Just to give you a reference, the world average is about 500 grams of CO2 per kilowatt hour. And if you trust the IPCC, you know, these are the big UN-led panels that get together periodically and try to see what kind of decarbonization is required for the different sectors of the economy to reach the 1.5 degrees C target. You need to decarbonize the electricity sector from 500, which is where we are now, to less than 50. So it's a big, big tall order. So let's see how they've done in Europe. And you can see that the 6 countries that actually have the lowest carbon footprint are Norway, Sweden, France, Switzerland, Finland, and Belgium. And if you compare the countries in the red box and the countries in the green box, you see that there is basically no overlap. The only country that shows up in both is Finland. And interestingly, Finland uses some biomass, not really solar and wind. But what do the countries at the bottom have in common? They have been able to decarbonize quite nicely their electricity grid, either by nuclear or hydro, or a combination of both. So empirically, what has worked best in Europe is a combination of nuclear and hydro. So the implication of this is that the first priority for countries in Europe, but everywhere in the world, if they have nuclear power plants, is don't shut them down. Because we've seen, for example, here in the US, in states like Vermont, Wisconsin, Massachusetts, California, Iowa, etc., that when you shut down an existing nuclear power plant, it is typically replaced with natural gas and a little bit of renewables, and the emissions will go up. There is just no way around that. So when you shut down nuclear power plants, emissions go up. We wanted to look at this not just from an environmental point of view, but also from a cost point of view. And so we looked at the example of Spain, which is an interesting one. Spain has about 7 gigawatts, 7 reactors now operating. Their licenses will expire, over the next 10 years. And the question is, do you make the investment to extend those licenses for another 20 years? Or do you shut them down? And if you want to keep the emissions at a constant, you need to replace them entirely with solar and wind and storage, obviously, to accommodate the intermittency. So the numbers look like that table there in the middle, and let me just sort of parse them out for you. So the green box there are the numbers for the scenario where you're just relicensing the reactors. Okay, so it's not cheap, and basically it entails about 35 euros per megawatt hour additional cost of electricity. But you have to compare to the alternatives. The alternatives are those 4 scenarios on the right, and S7, W7, SW7, and WS7. What those refer to is all solar, all wind, 25 solar, 75% wind, and then 75 solar and 25% wind. And the best you can do with those scenarios is an increase in cost of about $61 or euros per megawatt hour. So roughly double the cost of the nuclear scenario. So this is an important study or an analysis because it shows that not only makes environmental sense, but it also makes economic sense to basically maximize the value of the existing nuclear power plants. So don't shut them down. Really, that's absolutely the first priority. Now, I should say, sorry, before I move on this, this is not to argue that you don't want to put renewables online, but you put them in addition to nuclear, not in substitution. Now, doing a little bit of decarbonization is not that difficult, particularly for countries that have coal-fired plants. You shut them down, replace them with natural gas, and the emissions will go down a little bit. Maybe you bring in some renewables as well, and the emissions will go down a little bit. But the key issue here is how do you do deep decarbonization? Because again, remember, in the on the electric grid, in the electric sector, we need to basically go down by an order of magnitude in emissions. So that's what we call deep decarbonization. So what we've done at MIT is a study of many different regions of the world. And the one I'm going to show you here is a large province or a large region around Beijing in China, where we looked at the optimal generation mix, electricity generation mix, for different uh, decarbonization targets. So we have a model that has been validated, has developed and been validated for several years now. It's called GenX, that basically takes the demand, the hourly demand for electricity in a particular region. It combines it with the weather patterns in that region. So how much wind and solar can you rely on at any given time, at any given hour throughout the year? It combines it also with the cost of construction, operation, maintenance, and fuel for the different generators on the grid. And out it comes the optimal generation mix, whereby optimal it means the generation mix that minimizes the average generation cost. So the y-axis here that you need to pay attention to is dollars per megawatt hour. So that's the average cost of electricity in that system. And then the other variable that you look at is the x-axis. That's basically the decarbonization target. So the model allows you to say, okay, I want a generation mix that meets the demand at any given hour throughout the year. And it also does not emit more than, say, 50 grams of CO2 per kilowatt hour. So you can run this model for these different decarbonization targets, and you can also run them for different scenarios, which are shown here in two colors. One is blue and the other one is orange. And blue means nuclear is not allowed to play. In other words, that mix does not have any nuclear, so you exclude it from the mix a priori. And then the orange says nuclear and nominal cost. And there is a third scenario that we looked at, nuclear lower cost by 20%. And what you can see now, you can finally look at sort of this plot here and try to understand what it tells us. What this tells us is that the scenarios without nuclear, which are shown in blue here, tend to have an average cost of electricity, which escalates quite rapidly as you're trying to deeper and deeper decarbonize your grid. And you can see it goes up by factor 2, factor 3. If you go up to, if you really want to do complete decarbonization, it goes up by a factor 4. Now, why is that? Well, the answer is in these plots here, which are even more difficult to read because the font is small. But these are now installed capacity. What does that mean? It tells you how much, what is the share of the different technologies on your grid. And so the plot at the top is for the no nuclear scenarios, and the plot at the bottom is for the scenarios with nuclear. And let's focus first on the top plot. If you exclude nuclear, your overall capacity has to grow dramatically as you try to decarbonize. Because if you're trying to decarbonize without nuclear, you're left with having to build a lot of solar, a lot of wind, and because of the intermittency, a lot of storage. And it's the aggregate cost of all those overbuilt infrastructures that really brings the average cost of electricity up quite a bit. Now, the scales here matter, so you should pay attention to the numbers. In the top plot, the numbers go from about 100,000 megawatt to about 90,000 megawatts. At the bottom, the numbers are one order of magnitude smaller. So for the scenarios with nuclear, the overall capacity installed remains more or less at around 80,000 megawatts. So it does not escalate at all. And it has to do with the fact that nuclear, of course, is a dispatchable. It's not only low carbon, but it's also dispatchable. In other words, you can control when you get the energy that you need. So the bottom line of this whole study that we did is that an effective and efficient and rational decarbonized grid would actually include a lot of nuclear. And so that's, that provides the motivation for saying, okay, we're going to need more nuclear. Now, what's the problem? So why aren't we building nuclear plants left and right like there is no tomorrow? Well, the problem, let me just give you the punchline before I walk you through this table, is that they're too expensive. It's really cost. Now, there are other challenges for nuclear, no doubt about that. But if they were cost competitive, we would be building a lot of nuclear power plants in the US, in Western Europe, everywhere. So why are they expensive? Well, I call this a perfect storm of unfortunate attributes. So as part of a study that we did a few years back at MIT, we compared the nuclear industry to other major industries. And we did that according to 4 categories. First, the system size. What is the size of the machine, if you wish, or the system at the heart of that industry? So a nuclear plant, a traditional nuclear plant, is a big machine. Gigawatt scale, sits on like a square kilometer. Lots of civil works, a lot of concrete, big system. It's not unique in that sense. Chemical plants are also large. Offshore oil and gas platforms are large, but you have a big distribution here. You have other industries that rely on machines that are very small, automobiles, jet engines, consumer robotics, etc. The second category was factory fabrication. Are these machines produced, in a high productivity environment, such as a factory, or are they built, assembled in a low productivity environment like a construction site? Again, nuclear, unfortunately, traditionally is a construction site based technology. Not unique, but there are other technologies that are very heavily factory based. Number three is the licensing of a new product in that industry based on a lengthy testing requiring the demonstration of a safety case. Very lengthy for nuclear, not unique. If you are into jet engines or pharmaceuticals or automobiles, also very long. But at the other side of the spectrum, consumer robotics, coal plants, not that long. Last but not least is the product produced by these machines, a high return product, a high value product, or it's a commodity. Well, for nuclear plants, traditionally, they're connected to the grid. Once the electrons are on the grid, nobody cares where they're coming from. It's the ultimate commodity. It's a very, very cheap, low price market. Again, not unique, but on the other end, you have things like automobiles. If you want to buy a BMW or a Ferrari or whatever, you want that model, you're willing to pay a premium to buy that car, although the functionalities might be similar to another car. So it's a non-commodity market. Again, big difference. The bottom line of all of this is that the innovation cycle for nuclear, because of these reasons, has ballooned to order of 15, 20 years and cost the order of $10 billion. This is effectively the cost and the time required to bring a new nuclear technology to market. Now, I don't need to tell you that if in this day and age you go to a bunch of investors and ask for $10 billion with the promise that maybe 10, 15, 20 years later you're going to make a profit, you're going to be laughed out of the room. So this model is no longer sustainable. That's really the bottom line. All right, so what are the solutions? Well, I'm going to tell you about a potential solution. Potential solution relies on the fact that we need to shift the paradigm for nuclear development, deployment, dramatically, 180 degrees. First, the machines have to be smaller and more serially manufactured. The model, in my opinion, is jet engines. Jet engines are actually small power plants. At takeoff, a jet engine generates about 50 megawatt of mechanical work. It's built in a factory, as is shown in the figure here up on the upright, and it costs about $50 million. And by the way, it's a complex and delicate machine. It's not a nuclear reactor, but it's not a simple, super rugged machine. So it has the level of complexity that you might envision for small micro reactors, which we're going to talk about later on. So first, smaller, serially manufactured machines. Number two, we need an accelerated testing and licensing. It's absolutely not sustainable to take 10 years to go through a licensing process for a new reactor. And number three, very, very important, why limit nuclear only to grid connected electrons? There are many other markets that I will illustrate where a nuclear can actually command a premium, a higher added value. Okay, and so economically much, much more attractive for investors. All right, so smaller systems. I think the industry basically gets this. There is a lot of excitement about small modular reactors like NuScale or BWRX-300. Those are essentially miniaturized light water reactors, 300 megawatts and less. They tend to be simplified in design. They tend to have passive safety. All of that is good. There is also interest in high temperature gas cool reactors. The Chinese, I think this year, will finally bring online 2 units, HTGR modular, about 200 megawatts. So that's now available technology. Interesting technology. You can deliver heat at 650, 700 degrees C. That opens up some other markets. I think we should absolutely pursue these smaller machines. However, there is a big catch here. According to our studies, which I think at this point have been validated, about half of the total cost of a new nuclear power plant is in construction. It's in the civil works. It's in the site preparation, the excavation, the foundations, concrete, all of that, the labor associated with it. And unfortunately, these reactors, they might be modularized and be factory made in terms of the reactor components, but they still entail a large construction site for their deployment in the field. So I think that's a little bit of an Achilles heel for these small modular reactors in HTGR. And that limits the amount of cost savings that you can achieve with these machines. But absolutely, we should pursue them, in my opinion, more promising than the large light water reactors. Or you can go to very, very small systems. And I know at, here at Illinois, you guys have been talking about this. This is not going to be a surprise. So these are the microreactors, but I'm going to call them nuclear batteries because they're really not just microreactors. They're microreactors with a certain set of features that make them ideal for penetrating new markets. So what is a nuclear battery? Well, it is a microreactor. So let's say that it generates between 1 and maybe 20 megawatts. It's both heat and electricity. Crucially, it's not just electricity, it's heat. A nuclear reactor generates heat to begin with. A lot of markets require heat, as I will explain later. It's obviously carbon-free because that's nuclear. I think they have to be designed to be dry cool so that they don't require any cooling water. That makes them geographically less constrained. They're standardized reactor design. They're absolutely factory built. Remember, the scale is a jet engine, and if you look at that image up there on the slide, you can see that that's exactly the scale we're talking about. So a machine of that type can be built entirely in a factory. It is deployed or delivered to the site in a standard container. It has some kind of energy conversion cycle. It could be an air breathing gas turbine or a small Rankine cycle. It's plug and play, standardized connection. So you're talking days, weeks, maybe a month to connect it to your local users, not the usual, 5 or 6 years construction project. For economic reasons, it has to be autonomous or semi-autonomous operation because it generates only a few megawatts. You cannot afford to have 100 or 50 or even 20 operators on site. It has to be basically an autonomous system. Interestingly, it has to be designed to be on-site, off-site refueled. So maybe it can operate between 3 and 10 years, just to be on the generous side, without refueling. So the customer gets the nuclear battery on the site, uses the electricity or the heat, and then once the battery is exhausted, so to speak, that battery is sent back to a central facility where it's refueled and refurbished. The very important implication of this is that there is no need for on-site handling or storage of radioactive material. So the customer doesn't have to mess with either the front or the back end of the fuel cycle, which also from a proliferation point of view is a good thing. So these are some examples of the nuclear battery designs that are being developed. Westinghouse is one, Core Power, this is for marine applications. Holosgen was proposed for the Army. At Illinois, you looked at USNC, which is another one. And then my favorite, for the simple reason that has already been demonstrated, is a nuclear battery for space applications. It's called Kilo Power. And NASA and Los Alamos designed, fabricated, and tested this for less than $20 million and less than 3 years between 2015 and 2018. So this can be done. And these are the scales that we're talking about. We're talking less than $100 million, maybe $100 million, and less than half a decade, not 10, 20 years as usual. So what is unique about these batteries? Well, they're uniquely compact and reliable with respect to low carbon alternatives. What is shown here is with that little yellow rectangle, that would be the physical scale, the physical size of a 10 megawatt nuclear battery. And you should compare that to a wind turbine that nominally can give you 10 megawatt or a solar field that could give you also nominally 10 megawatts. So again, huge difference in scale, in physical scale. This, by the way, makes them also geographically constrained. You could deploy these virtually anywhere, everywhere, geographically. It is suitable for mobile deployment if there are applications that require that, for example, ship propulsion. And it has a predictable generation cost over the lifetime of the asset. Once it's built, then you know how much your electricity or heat are gonna cost over the lifetime of the machine. And then they have to be designed to be really ultra safe, rugged, robust, to be deployed in urban environments, semi-urban environments, and so on. All right, so the nuclear battery is actually not an entirely new idea. Back in the 1960s, the U.S. Army, actually did have some nuclear batteries. They didn't call them nuclear batteries, but they were portable reactors of the order of a megawatt, a couple of megawatts. What has changed since the 1960s to now is that a whole suite of technologies that can actually enable the design and construction of a modern nuclear battery. So these are things like advanced gas turbines, additive manufacturing, new materials and sensors, robotics, artificial intelligence, et cetera, et cetera, et cetera. All of that is going to contribute positively to the development of a nuclear battery for the 21st century. And then also what gives me hope that this is feasible is that there are massive synergies with other DOE, other government programs in the United States in particular, that are aimed at developing advanced reactors in general. And so there is money, there is motivation, there is support, bipartisan support in Congress. A DOE program itself has DOE, has a program for advanced reactor demonstration at the Idaho National Lab, among other sites. The Army program for microreactors also put several $100 million on the table, and then NASA, which I already mentioned. Now, where would the accelerated testing and licensing come from? Well, it comes from the superior safety profile, if you wish, of these machines. And what do I mean by that? If you're familiar with traditional light water reactors, and even the newer versions like AP1000 and so on, you recognize here on the left some of the features that makes these machines uniquely robust. First of all, there is no need for emergency AC power to deal with decay heat removal or reactor shutdown. There is no need for operator intervention. The designs are simplified and the operations are simplified, so there are fewer chances for human error. And then last but not least, the emergency planning zone can be limited to site boundary. That's because the source term and the barriers, the containment structure and the fuel forms are such that under no credible scenario you would have a significant release of radioactivity into the environment. So once again, the model is this kilopower crusting by NASA and Los Alamos that I mentioned, and that was, like I said, tested in 3 years. So this can save literally a decade and an early $1 billion. And if you're familiar with sort of investment dynamics and startups and so on, the so-called value of death in the first few years, it's one of the biggest hurdle to get over with. And if your value of death is not a decade and $1 billion, but it's 3 years and $100 million, that changes things quite dramatically. Now, the last piece here of the puzzle is how do I add value to the products from a nuclear battery or from nuclear in general? So higher added value can come from one of two scenarios. One is there is a strong policy signal that recognizes that nuclear electricity is more desirable than other forms of electricity or heat, because it's non-emitting, because of its high economic impact, because it's stable, because it contributes to energy security, etc. Well, that's all good, but it's unlikely that governments will suddenly fall in love with nuclear. And frankly, it's completely beyond our control as nuclear engineers. The second option is much more interesting because it relies on capturing new markets. Once again, don't think power grid only, think beyond. And this is within reach with the right technology. And I would argue that these nuclear batteries are the right technology for capturing new markets. So let me tell you a little bit about that. I'm going to call this beyond the grid. All right, so first of all, why does this matter? Well, the debate on decarbonization has disproportionately focused on the grid. But if you look at this pie chart, which shows the relative share of emissions, CO2 or greenhouse gas equivalent emissions in the economy, only about a quarter comes from electricity. 3/4 come from other sectors of the economy, things like industry, transportation, buildings, agriculture. Now, you might argue that some of these sectors can be, or some activities within these sectors can be electrified and therefore, redirected back to the electric grid. But mostly actually cannot be electrified, and it would not be economically competitive to electrify. So we need to look at the grid, but also beyond the grid. Absolutely, there is much more than the grid. All right, so what are we talking about? Well, first of all, heat more than electricity. It's a much, much bigger market. Factories, more often than not, require heat. They don't require electricity. Huge market. Transportation, charging stations for electric trucks or hydrogen vehicles. Electricity and hydrogen are not primary energy sources. They are energy carriers. They require a primary energy source to produce them. Nuclear can do that. Nuclear batteries can do that. District heating, desalination, microgrids of all types, whether it's towns, islands, military bases. We're going to need a lot of big pumps for flood protection, particularly coastal communities because of rising sea levels. It's going to be a big market. Freight ships, propulsion. That is an industry that has committed to pretty serious CO2 emissions over the next 10, 15 years. And nuclear is one of 3 technologies that they are seriously interested in pursuing for propulsion of freight ships. Data centers, farms, not obviously the traditional open air farms, but containerized or portable farms, which are also called aquaponics or hydroponics. Indoor aquaculture, fresh fish. This is one of my favorite applications. In Dubai, they currently get half of their fresh salmon needs from local aquaculture. So made in Dubai or raised in Dubai salmon, which is incredible if you've ever been there. It's the last place on earth where we just pack salmon to thrive. But of course, it's all indoor, and so it requires a lot of electricity for cooling and pumping water around. Biopharma, portable biopharma for synthetic insulin vaccines requires raw materials and electricity. Portable 3D printers, and then of course, space applications where nuclear can play a big role. So all these can be potentially accessed by nuclear batteries. And the point that I want to make here is that the supply of heat and electricity for all these applications would not require the deployment of massive transmission and storage infrastructure, as is the case with renewables and fossil fuels, because here you would have these nuclear batteries basically co-located with their customers. So they would be at the same site where that energy is used. So it really obviates the need for a lot of additional infrastructure. So to be even more specific, I did a study with the PNNL, Pacific Northwest National Lab, a few months back for the state of Washington, and we were looking for potential heat applications for nuclear batteries in the state of Washington. And we went systematically through all the different industrial sites in that state. And this table only shows, I think, 20 or 30 out of over 100 that we found that would be almost ideally suited for nuclear batteries, because their average heat load 24/7 is of the order of, between say 5 and few tens of megawatt, which is precisely where the nuclear batteries would be operating. And these are very mundane industries, and they need heat, and currently they just burn natural gas. And the idea here would be to replace natural gas with a nuclear battery. So you can see here things like food processing, university campuses, University of Illinois. You guys have been discussing the possibility of putting a microreactor on campus. Perfect application. Paper board mills, pulp, et cetera, et cetera. So there's many, many, many different opportunities. What are the cost targets? So if you're selling electricity to these customers, then what is sort of the range of electricity cost where you're going to be competitive? Well, the main competition will be the grid, unless you are in the middle of nowhere. If you are in an urban, semi-urban environment, you will probably be close to a node on the grid. But of course, nuclear batteries are not on the grid. They're competing with the grid, but they're not on the grid, because they obviate the need for transmission and distribution. Their generation cost must be compared to retail prices, not to the generation cost of other generators on the grid. So if you look at retail prices for electricity last year or a year and a half ago or so, including generation, transmission, and distribution, these are the numbers for different sectors and for different regions in the US. I'm not going to go over these numbers. The bottom line is that if you can generate electricity for $70 to $100 per megawatt hour in the United States, you're actually going to be directly to customers. You're actually going to be competitive with the grid, against the grid. So that should be your target. What about heat? Well, heat is a different beast. We don't have a national grid for heat. Heat is always sort of locally generated. And the main competition there is natural gas fire boilers. Now, natural gas is pretty darn cheap in the US, okay? So this is a tall order. So I'm going to show you what the numbers look like. Now, the good news, or I guess good news for the nuclear batteries, is that natural gas boilers are too small for carbon capture and sequestration. So burning natural gas will incur a carbon tax if you are in a carbon-constrained world, okay? So this is what the numbers look like. So on the y-axis, we have the cost of heat in dollars per megawatt hour heat, and on the x-axis, you have the price of natural gas in dollars per million BTU. The blue line at the bottom is the line without a carbon tax. Okay, and then if you add a carbon tax of $500, $150 per tons of CO2, then of course the cost of heat coming from burning natural gas goes up. And so this plot basically suggests that if you can produce heat at $20 to $50 per megawatt hour, which is equivalent to $6 to $15 per million BTU, then you're going to be competitive against natural gas boilers. So keep those numbers in mind. All right, so what are the economic imperatives for these nuclear batteries? Well, first, to access large markets, the nuclear battery must be licensable for deployment in population centers or near population centers. The markets that I shown you a few slides ago, those are not niche markets. Those are not middle of nowhere markets. Those are big markets, and they are in cities or near cities or coastal environments, etc. So you have to design a system that can be licensed and operated in a population center, essentially. From a cost point of view, we've done a levelized cost of electricity and a levelized cost of heat analysis, which suggests that the nuclear battery can meet the heat and electricity cost targets that I just described a few minutes ago, if the following happens. First, the power output has to be maximized within the nuclear battery constraint. So economy of scale applies also to very small reactors. What I mean by nuclear battery constraints, it means the system has to be truck transportable, for example, and the decay heat must be removed passively. Those are the constraints. Within those constraints, you still want the largest power output that you can get, because a lot of the costs are inversely proportional to the power output. The second requirement there is that the size of the staff is minimized. Again, you cannot afford to have a lot of operators for these machines. And the current fleet of nuclear power plants runs at around 0.5 full-time employees, FTEs, per megawatt. For these nuclear batteries, maybe you can afford a little bit more, 0.5 to 1.5, doesn't break the bank. But you do the math. If you have a machine that generates 10 megawatts and you have 1.5 FTE per megawatts, that means the most you can afford is 15 employees per reactor. Okay, if you go above that, forget it. You're not going to be able to meet those cost targets. Number 3, enrichment has to be low enrichment, not just LEU. LEU by definition is less than 20%. It has to be really low. If you ask me, 5%, which is what we already use now. Okay, don't go above that. Burnup has to be decent, as I say, over 20, maybe 30 megawatt day per kilogram. You don't need very high burnup, but you cannot afford. I've seen some designs that have 5 megawatt day per kilogram burnup. That's going to kill your economics. And then lastly, of course, the fabrication cost has to be reasonable, less than $5,000 per kilowatt. Once again, think about the jet engines. They cost of the order 20. A large jet engine costs $25 million, and it generates 50 megawatt at mechanical work at takeoff. That amounts to $500 per kilowatt. That's $500 per kilowatt. That's pretty darn cheap. And here we're making the assumption that our nuclear batteries have to be they have to be $5,000 per kilowatt, an order of magnitude higher. Okay, so I think this is quite feasible. But cost can easily get out of hand for small reactors. So what I'm going to show you now is a comparison between my baseline design, which is completely notional, and then an example of an expensive design. And since I don't want to put anybody on the spot, I don't mention here which company is this, but you can do a search and find out. Some reactors out there have characteristics that are similar to the column on the right. So the baseline design is 10 megawatts, MB fabrication, $3,000 per kilowatt. The fuel is $500 per kilogram, which is twice what we pay now for UO2. So again, very reasonable assumption. Enrichment 5%, burn up 20 megawatt, refueling interval 5 years, number of FTEs 5. On the right, you have the expensive design. People love to go to these micro machines, 1 megawatt, 2 megawatts, too small. It's going to kill you. You need to produce at least 10 megawatts or something like that. 20 megawatts would be even better, but 2 megawatts it is. Okay, fine. $7,000 per kilowatt. You read the assumptions here, pretty different. Okay, so now I'm going to show you what it does to your cost. Blue is the baseline case. You add it all up, you get to about $70 per megawatt hour. If you remember, the cost target for the nuclear batteries for electricity is between 70 and 100. So you would be comfortably within that cost range. So that's pretty good news. But if you don't do a good job with your design and you start using expensive fuel and very, very small power output, look at what happens to the different components of the cost. The fuel is twice as high. The operation and maintenance goes up by a factor of 10. The capex goes up by a factor of 2.5. You add them all up, and your LCOE, which is levelized cost of electricity, is now 4 times high. So things can get out of hand quite easily if you don't pay attention to design choices. Okay, so that's, if you're into microreactors, you're having fun doing neutronics, thermohydraulics, keep these numbers in mind. It has to make sense from an economic point of view. All right, so I think I'm going to close here, and then we have plenty of time for questions. And so this is somewhat provocative. I spent over 20 years of my career in nuclear, and I love the traditional plants. Okay, the one on top there is Flamanville. When the French will finally finish that reactor, that will have taken over 10 years to build that reactor. But it's going to produce an enormous amount of electricity. God bless them. It's a great machine. But 10 years, $10 billion, it's no longer sustainable, I think, in the US and Western Europe. Countries in Asia, Middle East, they're good. They build large nuclear power plants. They deliver them on time, on budget. God bless them. Keep building them. But in the U.S., maybe the future of nuclear looks more like that machine that I'm showing at the bottom there. So sleek, small, factory built, and can deploy in weeks or months as opposed to 2 years. So with that, let's see if there are any questions.
Thank you very much, Professor Buongiorno. I'm really excited to see that you and many of the Illinois folks share the same vision and excitement about the smaller reactors, microreactors on nuclear batteries. Okay, with that, I'm gonna open the floor for questions. Any questions from the students?
By the way, incredibly, I kept to time, 40 minutes.
Yeah, perfect timing.
I'm very proud.
Any questions from the students? Well, waiting for the students to think about the question, let me ask you one question. So in order to achieve the goals that you set up here, what are the main technological challenges that you see at this stage that needs R&D, especially at the university level?
Yeah, that's an excellent question. Let me use this slide to maybe guide the conversation a little bit. So as far as the nuclear technology is concerned, in order to get a compact core with a good neutron economy, we're going to need a good moderator. You can't go with graphite. The power density is going to be just too low. And so you end up with a large core, or for a given constraint, because of track transportability, you're going to end up with a very small reactor power, and that kills you on economics. So a solid moderator or a high efficiency moderator, which of course is not water, because you have to be able to operate these machines at higher temperatures, that is an imperative, I would say, number one. Fuel-wise, I am hot on 5% UO2. I know it's not sexy. I know it's it's what we've been using for 50 years, but that's what makes it attractive. We know exactly how much it's going to cost, how to build it, how to fabricate it, of course, and sure, it's going to limit you in burnup, but this idea that these machines have to operate for 10 or 20 years without refueling, to me is not valid. I think if you can deliver a nuclear battery to a site and let it run for 5 years, that's good enough. In 5 years, you bring in another one, and your customer has continuity of service that way. I'm not a fan of a very, very long refueling cycle. And by the way, from an economic point of view, the longer the refueling cycle, the more you pay for the fuel. So again, that doesn't make much sense. Now, on the let's see what else. On the nuclear side, not much else. I think if you stick with stainless steels or nickel alloys that are already qualified from the ASME code, you probably are going to be able to put one of these machines online within the next 3 years. So there are no big showstoppers there. On the Banzo plant, interestingly, this is a technology that is going to require a very easy, simple power conversion unit. So simple that it will have to be developed. Let me explain what I mean. If you have a reactor that operates at 600 degrees C and you want to use an air-breathing gas turbine, unfortunately, you cannot pick it off the shelf because most gas turbines operate at much higher temperatures. So they're optimized for a harsher environment than what they're going to see here. So there is going to be a little bit of development work required to downgrade those gas turbines to the operation conditions that are required here. So a little bit of that R&D. It's not research. It's really development is going to be required. If you decide to go with a Rankine cycle, I think it could be off the shelf, and it's going to be tiny. There are not that many Rankine cycles out there for 5 or 10 megawatts. So those are the things that come to mind on the technology side. On the policy and regulations, well, there is no shortage of interesting questions there, right? Starting with security, which is going to be probably the toughest nut to crack for these things, because if you want to put this in a shopping mall or in the basement of a high rise, well, regulations are going to be challenging, no doubt about that. But for example, a factory, I think it's a lower bar because it already has built-in security. So we'll see how it goes. Yeah. No, again, no shortage of interesting questions. Good question.
This reminds me, how about the load following side? Do you envision any like on-site energy storage solutions?
Well, I'm full of opinions, so I'm going to give you my opinion. No, because economically it doesn't make much sense. So it's a necessary evil. We were talking about this with Professor Huff just an hour ago. So if you are on the grid,
Hello? Is it me or Professor Buongiorno?
I promise I didn't mute him. He looks frozen.
Yeah, his is frozen.
Are you back?
Oh, I think you're back. Okay.
Awesome.
Yeah, you were frozen for like a few seconds.
Okay. Can you hear me?
Yeah, now it's good.
Can you hear me now? Okay.
Yes.
Oh, I don't know how much you missed my pearls of wisdom, but I was going to say, if
all of them.
if you're co-located with a customer, you probably want to choose a customer that wants that energy all the time, right? I mentioned factories. Very often they are 24/7 operation. Or maybe you are located in an industrial park that has several different facilities, but combined, you want to maximize the utilization of your reactor because that's good for economics, right? Absolutely. You want a high capacity factor. So do you need storage? Well, again, if it's absolutely necessary, put it there. But otherwise, I would rather just generate heat and electricity and just it goes off to the end users right away.
Thank you very much. Okay. Any questions from the students or faculty?
I have one since the students are silent. So you had this great table of dozens of potential heat applications. Very cool stuff. Exciting. My question is this, and maybe you mentioned it, and forgive me if I missed it. You list it looks like you looked at the heat load. My question is this: Did you do any categorization about the temperature at which these processes occur? Because
yeah, absolutely. Now that's a great question. So we had two filters in this analysis. The first was your demand is at least a few megawatts, right? If you only need 100 kilowatts, well, maybe a nuclear battery is not for you. But if you need 10 megawatts, 20 megawatts, as you can see the numbers here on the right, then that's the right range. That was the first filter. The second filter was exactly what you were asking, Kathy, which is, of course, at what temperature do you need that heat? And in all these applications that we ended up down selecting, we assumed that they need heat at less than 500 degrees C. So clearly, if you go with an LWR, you're not going to be able to meet that demand. In some cases, you are, by the way. Paper and pulp, they need 120, 130 degrees C. In other cases, you can't. But this was all less than 500 degrees C. And so at that temperature, by the way, you get a big chunk of the market. You obviously don't get it all because things like steel mills and cement, those are too high. So you wouldn't be able to catch those. But these mundane things, I learned that Washington is the world capital of potato, of fried potato, because they have a lot of potatoes in the state and Idaho. And so they have all these potato processing plants and they use heat all the time. They're on 24/7. They burn a lot of natural gas. So why not putting a nice nuclear battery on site, right? Good question. Yeah.
Thank you.
Okay. Any other questions? You can either raise your hand or just unmute yourself and speak. We have many students that cannot, in case you missed your hand.
Can I go?
Yeah, go ahead, Wenqi.
Thanks for your presentation, Professor Buongiorno. Just wondering, so I think there's one question I think thinking in my mind about the nuclear batteries is applicable to the current mobile system. For example, by car and auto cars, so that when we when we have the car running on the road, we can use a nuclear battery. But I think we need to think about if the accident happens, is there any system or something procedure we can make sure those radiological didn't release from outside the environment?
Yeah. So just to be clear, if you see my cursor here, it says electric trucks, hydrogen vehicles. What I mean by that is charging stations. I'm not proposing that the cars and the trucks would run with batteries. I'm saying that they along the highway, so to speak, you would have charging stations. Those charging stations are powered by nuclear batteries. By the way, this is the drawing here, the image. It's actually an Argonne National Lab proposal. It's not my idea. And they for big interstate system, if you are serious about converting heavy transportation, like heavy trucks, from fossil fuels to low carbon alternatives, then you can envision that you would have these sort of charging stations at set locations, and the trucks would just go in and basically refill either hydrogen, or if they're electric trucks, they recharge their batteries and off they go. So that's the idea. So now, having said that, of course, the safety and security of the nuclear battery at the recharging station has to be proven and has to be ensured. But that's true for all of these applications. The mobile application that I was talking about is actually the ships. And the ship, for propulsion in that case, yes, the nuclear battery is on board the ship. And basically it's in the engine room for the ship. But that's a different system.
Okay, thank you.
Okay, can I have a question? So, hello, can I have a question?
Yeah, go ahead.
I can hear you. Yeah.
Okay, so I would like to follow by the previous question. I would like to ask, do you envision any significant change when electrical car becomes dominant?
What kind of change are you referring to?
Oh, okay. The composition, the percentage of different energy sources.
I see.
Yeah.
Well, so if maybe I have it in the. Let me see if I have it in the backup slides. I usually show. Yes, over here. This is the one I wanted. So, how much electricity are you going to need to decarbonize the transportation sector? The answer is a lot. And the numbers are shown here for different countries. So in the US alone, if you were to convert all our transportation sector, everything, cars, trucks in particular, but here just for good, I throw in also air and water and sea, 285 gigawatts of new electricity. That's a big number. If you want to go with hydrogen instead of electricity, the numbers are even bigger. Again, remember, hydrogen is not a primary energy source. It doesn't, we don't mine it, we don't harvest it, we got to produce it from a primary energy source. So in that case, it's going to require about 100 gigawatts of heat and then 340 gigawatts of electricity. And the numbers are obviously smaller for other countries just because they have a smaller economy. But they're all big numbers, relatively speaking. So where is all this energy coming from? Well, it's got to come out of primary energy sources, nuclear, natural gas, solar, wind, geothermal, etc. So the short answer is that, yes, we'll change because we'll need a lot more electricity if we want to electrify the transportation sector. And that energy has to come from somewhere. So my hope is that a good chunk of that new energy will come from nuclear.
I see. Thank you.
Okay, any more questions? Okay, I don't see any. Well, thank you again, Professor Buongiorno. It's a great pleasure for us to have you here and hear about your vision on the future of the nuclear industry.
Well, thank you so much, and nice to meet you all, although just virtually.
Yeah, hope we can bring you to campus sometime, when we are able to bring guests to campus. A lot of exciting projects going on related to microreactors, small reactors.
I know, it's a promise. It will happen. Have a nice evening, everybody.
Okay, thank you very much.
Bye-bye.
Bye, everyone.